So, hello everyone, my name is Akshay and welcome to our channel of just GFG POTD streak of day 92. And if you're new to this channel, please like, share, and subscribe so that we can learn and grow together and maintain our streak. So, today's question is it's a medium category, medium X or A, and it's actually a good question. If I talk personally about me, I started solving it at 12 a.m. and I recently completed all the dry runs. Like, it took me more than 1 hour, to be precise, 1 hour 10 minutes, solve this question. Okay, so let's start this question and listen to this video very carefully. There will be a bunch of test cases here that I need to explain you first so that we can code it. Also, in the previous question that we had in this day 84 count lucky permutation, so in this we were using DP with bit masking, right? In this question we have to utilize the technique of bit masking, right? And why is this bit masking used? I already explained you that it was used to get to check if the ith bit is set or not in O of 1, right? That's the main use case of bit masking. Okay, so let's read the question and try to figure it out, what it is saying and what is the possible solution. So listen to it very carefully. So given two integers a and b, the task is to find an integer x such that x XOR a is minimum possible and the count of set b in x is equal to the count of set bits in b. Okay, and they have given the input test case like a equals to 3, b equals to 5, and they have not written any explanation, right? They have just thrown the question to you. So the XOR will be minimum when x equals to 3. Okay, that I also know that 3 XOR 3 is 0, but what's the intuition? In which direction should I think of? So everything is up to you. So 3 XOR 3 is 0, and the number of set bits 3 and 5 is uh, equal, right? That is 2. Similarly, in the case of 7 and 12, they are just saying that the minimum x equals to 6 and you will get the minimum as 1. And there is no hint that how to proceed on. So, okay, and constraint is 10 power 9 and that is O of log x max of a comma b. One thing I can see here is there is one hint here. So if I just dry run the test case for you, so we have this thing. I think you're able to understand the question, right? And let me tell you that how the input output is coming, how we can determine it, and then only we can code, right? So this is A and B, and we have this thing as 3 and 5. And if I do the binary representation, it will be 1 1 and it will be 1 0 1. And as if you see, then the number of set bits in A is equals to B. So let's represent it as SB1 and this as SB, right? And you can see that the number of bits are equal. Now what was the task? The task is to find an x such that x XOR a is the minimum possible answer. Minimum possible answer. Minimum possible answer can be 0. An integer that can be minimum possible is 0. And how we can achieve 0 using the OR? XOR, like I can say that XOR x is equals to 0 or y XOR y equals to 0. That the same number getting XOR with the same number, I can say it is 0, right? But how we can make sure this one condition that x or a should be minimum, at the same time the set bit count, or let's say set bit of x, should be equals to set bit of y, right? But I can see here that the set bit in 3 is actually equals to the set bit of 5. So I think there is nothing to do more in this particular test case where the number of set bit counts, set bit of a is equals to set bit of b. Then I just need to return this a, because why a? Because then only this 3 or 3 equals to 0, and 0 is the minimum possible answer, right? So you take any number where we have the equal number of set bits and a will be its answer. So if I just take another case where let's say it is 1 1 and 1, and this is 1 0 1 1, you can see that the number of set bits is 3, number of set bits 3. So if I write it in decimal format, what I can write it, that it is 4, then 6 and 7, it is 7, right? And if I write this as decimal format, it will be 8 plus 2 10 and then 11. So if I just compile run for this thing 7 and 11, the output will be 7. So let's verify that if we and this question are on the same page or not. So I will just input this dummy data and I will just run this to check that if is actually the thing which I am thinking, which I am explaining to you, is actually right or wrong. So, okay, 7 and 11. So let's compile and run. And as you can see, the 7 is returned, right? So we are in this current direction in this particular first in one test case, that if the set bits in this A and B are equal, then directly we have to return A, right? We can do that. Okay. Okay, so as we are going ahead, we will be coding it one by one, right? Because at the end, if I explain you all the logic and we then start coding, it will be like very difficult to understand, right? So we are confirm in this one case that if the set bits are same, then just return A, right? So let's make a function to count set bit. It will be static int count what set bit int n, and that's a very basic code, right? You just have to count the set bit, right? So I will just say while n is greater than equals to 0, and I will make a variable here int count equals to 0, and I will say that if n and 1 is not equals to 0, then you do count plus plus, and if not, and in every iteration I need to decrease the number by 2. So that's a very basic code, but still I'll tell you that how this is working. And let me code this first step, that if let me find this at bit 1 that points to actually A, and I call this function set bit A, and I will make one other thing as set bit that is for B, the set SB, and I will call the function again the set bit of B, and I will say that if SB1 is equals to SB, then return A, right? And let's check that also for this custom test case. Let's compile and run this code. And in this section, I didn't return the count, right? So it will throw me an error, return count. And also in Java, we cannot just compare like this. Whenever you are using binary operators, you have to put that thing in separate curly braces, right? Separate parentheses. So seems right to me now. Let's compile and run for this first test case. Okay, I'm missing return statement. So let me just return anything here. Let's say return 0. So see, as you can see, all our test cases will be passed if the set bits are equal, right? Because we have figured that logic that the minimum possible XOR is like the minimum possible XOR is possible only when you do the XOR of two same numbers, right? Okay, so that's good our first test case here, and let me explain you this how this set bit is getting count. So suppose we have this number as 101. What I if I am able to retrieve this bit, right? So if I'm able to, how I can retrieve that bit? Let's say I do it with and of 1, right? And what I can say that all these bits, since we are doing and with 0, all this will be retained as 0, and this 1 and 1 will become 1, right? And then what I'm doing, I'm reducing it by 2. So 101, if I convert this into decimal number and by 2, if I do it that, then I will get the remaining bits except the last bit. Then again I will do the and with 1, and as you can see the remaining will be 0, and you will getting the retained bit if you use the AND operator. So that's how it's going, right? Since if it is coming 1, that I'm saying that if it's not equals to 0, then count plus plus, else do not count it, right? Okay, so that's the very basic thing, but still I've explained that thing to you. Let me rub that. So let's see all the test cases quickly. I don't want to make this video very long. Okay, so from here I'm getting an intuition that okay, there may be some cases where set bits of A, right, which I'm storing as B1, right? And this I'm storing it as B. So there may be the cases where the SB1 will be greater, right? Will be greater, and then may be a case where the SB1 will be lower. Apart from these three cases, there is no other test case valid, right? All the possibilities are mingled up in these three test cases. So if I'm able to just found that how this greater than equality, how we are to think in that direction, and how we are to think in this less than equality, and simultaneously try to code it, then we'll be good to go, right? So if you see the second test case, so let's see what inequality equality it holds. So it is 7 and then 10. If I convert into what binary, then I will get it as 1 1 and 1, right? and then we have this, let's say, what, it was 12, right? So it will convert it as 1100. So here you can see that the number of set bits in A is greater than the number of set bits in B. You can see that, right? But before discussing this test case, I would like to discuss the another test case first. Where the another equality is holding, and for that thing, let me make a random example. Let me make an example that is 9 and 13, where 9 is actually, you can write it as 1001, and 13 you can write it as 1101, and you can see that the number of set bits in A is lesser than the number of set bits in B, and A is actually pointing as SB1 and B as SB, right? So this is the inequality holds there, right? So let's forget about the code. What is the thing that we can do here, right? What's the thing that we can do here? Okay, right? So that's the case here, and let's try solving both of these cases one by one. So I'm saying here, let me write one statement and then I'll explain it to you. I'm saying that if count of set bit in A is greater than the count of set bit in B, then I'm saying that the X will have the same number of set bit as A. X will have same set bit as A, right? And what we have to do, we have to change just change the least significant bit that is set to 1 to 0, right? until until and unless that until and unless that the count of until and unless the count of set bit in X is not equals to count of set bit in B, because that was a condition. We have to make the set bit equal, right? So what I'm saying that X is now 1 1 and 1, right? But actually the number is 2, right? The set bit count. So what I'm saying that I will traverse the least significant bit is this one, right? And let me tell you that what is least and most significant bit. So this is called least significant bit because it has the minimum value contributing to its decimal answer, because it has the contributing value as 2 power 0, and it has the contributing value as 2 into 2 power this all the number of numbers in the right hand direction, that is 2 power 3. That's why I'm saying the convert the least significant bit into 0. So if I convert it at 1 1 and 0, right? And this is was actually A, and I'm saying that this is X now, because you can see that the number of set bits and number of set bits are equal. And if I try to find the XOR, if I try to find the XOR, what it will be, that 1 and 0. So how the XOR works, so 1 and 0, so and 0 and 1, it gives 1, right? And if the same, then gives 0. If the same, then gives 0, right? So that's the reason I'm saying that we need to flip the digits, flip the bits from 0 to 1, so that we can get the least number, the least decimal number, right? So if we flip the bits from the least significant side, then only we can get the least decimal number, right? So 1 and 0 will become 1, and this will all become 0. And the minimum answer, that X or A here, is now pointing to 1. But suppose कि भैया I would not listen to you, I will just check कि if I'm reversing, if I'm flipping the most significant bit, then what's happening. So let's do it. So what I was saying, that A was 1 1 and 1, right? With this A only we'll get the answer in all our test cases, right? We have to do some manipulation there, and the number of count of set bit in B is 2. So I said that you flip the least significant bit from, that is from left to right. But you can argue me, no, let's do it from what this is left to right, right? And least significant is from right to left. Okay, so you can argue that let's do it from this left to right. Okay, so let's do it. So you get first one, and you have to flip it. Why you have to flip it? Because you require only 2 set bit, right? So you flipped it, and you leave the rest of it as same, because then you will get this count of set bit as 2, and you can say that this is now our X and this was actually our A, right? And we need to XOR the thing. So 1 XOR 1 will be 1, and it will be 0 and 0. And as you can see that A XOR X is equals to 8, and that's not is valid as per our question. We need to find the minimum XOR, right? So that means that we have to flip the one from the least significant side. And this is the answer actually. So this is X is actually the answer. And this is what equals to I guess it is equals to what? 4 and plus 2, that is 6, right? So let's check it. Let's check it from our compiler also. So the input was 7 and 12, right? Okay, so this was our second test is this was our second test case only. So you can see that the output is 6, right? Okay, so we have derived something for the inequality which is greater than also, right? Okay, so let's do one more example to understand it more thoroughly. So we were having this 7s triple one, right? So let's take 4 times 1 now. 1, 2, 3, and 4. So it is actually equals to what? 14. And let's take the same number as B as 12, that was 1100, right? So I can see now that there are only two ones here and there are four ones here, right? So what I can do is I need to flip the two ones into the two zero, right? And since you need the XOR, and the XOR behaves like one XOR, if there are unequal bits of the reverse nature, then the answer is one, right? And that's why we are traversing from the least significant bit, because if we flip it 0, then the answer will become here 1, right? And we don't want this 1 to come here at the most significant bit, because that will increase our a's or x, as we discussed in the above case. So there were two extra ones, right? So here it was count was 4 and here count was 2, so there are two extra ones. So just start traversing from this direction, from right to left, right? And you encountered one, flip it to 0. You encountered the second one, flip it to 0. And now there are actually two ones present here and two ones there, so just copy it here. So this is our a and this is our x. If you do the a's or x, it will be 1, 1 or 0, 1 or 0, it will be 1, and it will be 0 and 0. And if you see that this points to 3, right? So let's check this test this via our compiler. So we input the number 14 and 12, right? So let's check it, that if we are on the same page or not. So we input 14 and 12, right? So I need to pass it on a different line. 14 and 12. So let's check it, what the answer come, and we'll be able to rectify that if we are going in the right direction or not. So so the answer comes here as 12, right? So let us rectify in our dry run, did we get 12 or not, right? So this was our a and this was our x, and if we convert this x into this binary to decimal, it will be 2 into 3 power 8 plus 4, that is 12. Okay, so we are on the same page, guys. So this is the thing that we have to do if this inequality exists, that a is greater than b, right? So let's solve it now for when a is less than b. So why am I emphasizing so much time on this? Because understanding the input and output is very crucial here, because then only you will be able to code it, right? So again, pointing it out again, if you're new to this channel, if you like my content and the way of teaching, please subscribe it right now, so that we can grow together and learn together. So let's jump to the our third test case, that was actually saying that we have this thing as n equals to 9 and b equals to 13, right? Where the counter set bit in 13 is 3. So if I just write it, it is 3 and it is 2, right? So what we have to do next. So we have to make one more one here in this case, right? This is a, and we have to take one more one here. So the same logic holds here. If you make this 0 as 1, right, and you sustain all the bits as the previous one, then if you found the XOR, it will be 0 1, because since you have went to the most significant unset bit and then you have changed, so it will be 0 1 1 0, right? And if you convert in this in the binary system, in the decimal system, it will be what? 4 plus 2 6, right? But if I give you an argument that if we would have went from this was 1, this was a, right? If we would have went from this, from there, from the least significant bit, because we know that if we do the XOR after the flipping, we will get 1. So why not take the least significant bit, which has the lowest contribution in that decimal number? And that's what the question was saying, right? So we will flip it. So we will start from this point, from right to left. And as soon as we see that there is a number which is not 0, which is 0 actually. So we need one more one, right? This was 3 and here count was 2, so we need one more one. So I start from right to left, and whenever I found that the bit is 0, then what I will say that flip it, right? And now we have all three ones here and 1 0, so we have the all three ones, right? So this will be our a and this will be our x, right? So now we can found these or, and we can see for ourselves that the answer is getting minimum or not. So for one it will be 0 0 and 1 it will be 1 0 0 0 1 1 and 0. And as you can see that this is equals to 2, which is actually pointing to a or x, it equals to 2. And in the previous case where we were manipulating the bits from the most significant part, it was coming 6. So clearly we can see that in both the cases we need to traverse from right to left, and we need to change the least significant bit part. And as you can see for this 9 and 30, I can clearly say that my answer will be 1011, and if I convert into the decimal format it will be 11. So why not check it with the compiler also, so that we can verify that the question and our logic to solve it are on the same page. So I give the test case as 9 and the second was 13. So let's compile and run it. Great. So it is coming 11, right? Expected is 11, and we have found 11 from our dry run also. So great. Great, guys. So I think you are with me till here. So we have understand that how we have to proceed on with the all three equality cases, right? So one last thing now of the extended test case of this third one. So there may be a case where I can see that the number of ones was 3 here for this B, and the number of ones in 9 was 2, and the difference that is 3 minus 2 is 1. So I need one unset bit to flip, right? But what if the unset bit is equals to this the flip we want to the bit we want to flip? So what I'm saying is that suppose we have a test case of this thing, that 1 0 1, this is a, and this is b of 1 1 1 and 1. As you can see, the number of set bits here is 4 and the number of set bits here is 2, right? So you need to add at least 2 1 here, right? But as you can see that there is only 1 0. So I will traverse from here, I will see that there is 1. I'll just copy the bit if it's 1, and I encounter 0, I'll flip it and will turn it to 1. I encountered again 1, I do not have to touch it because I still need to complete my 4 ones, right? So now you can see that there are only 3 ones here. So what to do in this case? You need to add one more one here, then only you can do that, right? You need to add one more one here. So that was the extended test case of this third case, where was the set bit in b is greater than a. So if you find, so I'm saying that this is my a and this is my x, right? And I need to XOR with it a, whatever it comes. It didn't matter now, because that's the only smallest possibility we can give it to x. And if I convert it into the binary decimal number, so it will come as 8 plus 4 12 plus 2 14 and plus 1 15. So just verify it. So let's verify this thing also. So if I convert it is 5 and b is triple one, that is 15. So 5 and 15, according to our intuition, the answer should come as 15. So let's verify it, and then we will move to the coding section, because after this all the test cases we see for the dry run, we are like completely well to go to now code. Okay, so it's 15. So great, guys. So we are on the very good track. So let's code it. So coding will be derived from the dry run we just made, right? So what I was doing, let's code this case first, where the set bit was actually greater than a equals to where the b, right? So what I'm seeing here is I was traversing from right to left, and I was always saying that I always want to know that if the ith bit is set or not, if the ith bit is set or not. So I need to do that first. So my first problem is to check ith bit set or not. This is my first problem. And what's the length of this binary number? It is a 32-bit number, right? So if I start the code, I need to start the code with for I equals to 0 to I less than 32 I plus plus, right? That will be, or I, let's say, equals to I less than equals to 31. I can write this as this also. So this is where, to check the ith bit set or not, this is where bit masking comes in. This is where bit masking comes in. That tells you the thing in O of 1. How am I saying that? How am I saying that? If you have watched my day 84 videos, you must have been aware of this, how this works. But let me tell you again. So you nothing, you have to do nothing, right? So first let me tell you that if I say you that one, uh what this is, left shift I, then what does it mean? So what does it mean? 1 left shift 0, what does it mean? That 1 into 2 power 0, it means once 1, and if I convert into binary, it will be just 1. If I say 1 left shift 1, then what you will do, you will do 1 into 2 power 1, that gives us 2, and you will say that 1 0 is the thing of left shift 1. So if I do that 1 left shift 2, then you will do 1 into 2 power 2. You will write the decimal number as 4, and you convert it to binary as 100. Similarly, for 1 left shift 3, you will say that 1 into 2 power 3 is 8, and you will write the binary number as 1. Okay, so my Apex game install is popping up. Okay, so this is 8. This is the binary representation of it, 1 3 zeros. So observe this thing here. Suppose you have this number 1010, and I'm saying that I am this point, I am this second term, and I'm saying that can you find me this bit, this bit. I don't want to find the rest of it, if it's set or not. I just want to, I'm interested in this one, which is at the last second place. Then I can say, okay, give me 1 here and give me all zeros in the rest of the places, and I will do the AND operator, because this 0, if 1 is 0, every will be becoming 0 0 0 0, and if this thing is 1, right, so it will retain the above bit. The above will be, if it is 1, it will be copied as 1. The above bit, if it is 0, it will be copied as 0, right? And if you clearly observe, when I was finding the second bit is set or not, let's say this is n, I was actually doing that n and 1 left shift 2. This is what I actually did, right? And this is what actually bit masking is. It tells you if the kth bit is set or not using this thing, right? You can say that this is 1 left shift 2. You can say that, right? Okay. So how am I going to integrate this with our code? How am I going to integrate this code? Let me open a new page. Okay. So what should be the code of this? What should be the code of is to check if the ith bit is set or not. So let me write it for you. And I just showed you the right one that it was 1010, and if I chose to the second bit, then what I did, then I just copied the 2 thing, and I said that n and 1 left shift 2, right? But I need to do for each and every bit. So, and there was a for loop running for I equals to 0 to I less than equals to 31 I plus plus. So for each I, this is what is called mask. This is called mask. So I will make a variable int mask, which will be equals to 1 left shift I hope this is very clear to you, right? And I will say that I will make a variable int set, right? It is just checking that the bit is set or not. And what I was doing, n and 1 left shift 2, right? N is nothing but here it is a. In our case, we were checking for the a, right? And 2 is nothing but I, so I will just write it. I will write it 1 and what, 1 left shift I, and 1 left shift I have stored in this here, so I will say 1 and mask, right? So this will check the ith bit is set or not. So let me code this thing and we will proceed ahead. Okay, so let's make a variable now that it int answer equals to 0, and I will say that for int equals to I equals to what, 0, I less than equals to 31 I plus plus, and I will say that int mask for each I is equals to 1 left shift I, and int the last bit, I'm at my last bit now. From last bit I will go to the firstmost bit, that is I'm traversing from right part to left part, right? So I will say that if a and mask, that is it. So there was a case that if set bit is 0 and if set bit is not 0, right? If set bit is 0 and And what was our case? That SB1, what was our case? Let me go back again for you. So we were coding this third case, right? So you can see for this case, I was saying that SB is greater than SB1. So I will code it here, that SB is, or let's say SB1 is lesser than SB. So you can say that SB here was was greater than SB1. So this was the case, right? So if that's the case, what I was doing in my dry run, let's go and see. So if the set bit was equals to 0, let's say it was 0, then what I was doing, I was flipping it. I was flipping it and I was storing in my answer. And if you see that, what is this flip? This flip is actually the mask. If you just see, this flip is actually the mask, that is 1 0, right? Right? Okay. So let me give you one more try run. Okay. Okay. So what was our case? What was our test case? So 1 0 0 1. It was 1 0 0 1, right? Yes. And B was 1 1 0 1. 1 1 0 1. Okay. Great. So we were at this point. So for I equals to 0, what is happening? So for I equals to 0, I can say that we are doing mask, right? We are doing set equals to A and mask. So what is A here? A is 1001, right? And what is mask here? Mask is 1 left shift 0. That is nothing but that is 1, right? So I will do 0 0 0 and 1. I will do the AND operator. And as you can see that all because of this, all this 0, all the bits above will be converted to 0, and only this bit will be retained as the original 1. So this is 1, and what I was doing, whenever I was getting 1, whenever I was encountering 1, you remember, whenever I was encountering 1, I was just moving ahead. I was just searching for the 0 and then flipping it, right? As you may recall from our dry run, this is the thing we were doing. So what I need to do, I need to add this in my answer. I need to add this in my answer. So if set is equals to 0, right, equals to 0, and SB and SB1, this was the case, right? So we have to do something here, but in the rest of the case, I need this thing as my answer. So what I can do is, this is actually set, right? This is actually set, and I have maintained an answer. So if you have to include something in your answer using the binary wise operator, then what you do, you write this as answer is equals to answer or set, right? So how this is working, let me explain it to you again. So how this is working, so answer was equals to 0, right? And you did with with this set. So you did 0 or 1. So you have the answer as 1. You retain this thing, right? You retain this string in your answer. And what our goal was. Okay. So for I equals to 1, we went here. We are at this point. So we have the A as 1001 and we are at this point. I need to retain this bit. So the mask will be 1 left shift I, and I is pointing to 1, so that is equals to 2, right? And if you convert 2 in the binary, it will be like this. So all these bits, all these bits will be retained as 0 because we have passed the masking thing. It will be 0, and this bit, the original bit, will be retained as it is because we are using the AND operator. So it will be 0 here, right? It will be 0. And if the set is equals to 0, then what you need in your answer, then what is the thing that you need in your answer? You need this thing, right? You need this. If I just, you need this one. You need this one, right? Because this is the thing that you have flipped from 0 to 1. We have flipped it from 0 to 1, right? And that's what you want to include in your answer. So if set is equals to 0, then what you need to include in answer? That answer, if I was willing to include set, then I did answer equals to or answer or set. If I need to include mask, that this is actually mask, right? If I need to include mask, then on the same thing, I can say that answer is equals to answer or mask, right? And now the set bit here was in this, for I equals to 0, set bit 1, that was actually pointing to A, and the set bit B was to B. So here it was 3, and here you can see it was 2. But as you have converted, flipped from this 0 to 1, you can say that now the set bit in A is now 3, right? Or you can say that decrease this count. So I will say that set bit of 1 is 2, and you decrease this count, that I don't require, I have already taken one more here, I don't require uh, so you can, I have already taken one more here, so that means you need to decrease this requirement, right? So I can decrease it to 2, right? And now you can see that the 2 is now equals to 2, so it is balanced, right? It is balanced, but our answer is still not complete, our code is still yet to progress. But here I can say that as b minus minus, right? I hope you're getting this point. I'm explaining you each and every point, right? So for I equals to 2, let's run it. So a is actually equals to 1 0 0 1, and we are at this pointer. The mask will be equals to 1 left shift 2, that is nothing but 4. So I will write it as 4, this 0, and because of all these 0, the every bit above will be coming to 0, and only this bit will be retained. That's the power of masking. This is retained, and as you can see that the set bit is 0, set bit is 0, but you do not require now, you do not require, right? You do not require any more number of ones, because sb1 is already 2 and sb is already 2. You do not require any more ones in your a number, right? Okay, in your x number, in your x number, right? Okay. Okay. So what we can do, we need to just proceed ahead, right? We need to just proceed ahead. And if we need to proceed ahead, that means since we are not flipping this 0, then our answer should come from here, right? Our answer should come from here, because at the last time when we flipped it, we take the answer from this one, right? From the mask, because 0 was converted to 1. So it will fall into the else case automatically, because I have mentioned this condition. Because whenever you have this case, then only you do this thing, you take the mask as answer, so it will automatically fall into the else case and the answer. So here the answer first of all will be updated as previously it was 1, so copy it here, and it will be masked with 2, right? So 1 0, so it will be 1, and you have to do or operator. So it is 1 and 1. So the for I equals to 1, the answer is updated as 1 comma 1. So for I equals to 2, the answer will be updated as 1 1, and you need to XOR with this 0, right? This set. So let's XOR it. So it was 0 0 and 0, right? So it will be what? And this was also 0, right? So it will be what? It will be, if you do the XOR operator, it will be 1 1 0 0, right? Okay, so for I equals to 2, the answer is this one. For I equals to 3, let's solve it for I equals to 3. Our A was actually equals to 1 0 0 1, and we are at this point. So masking will be equals to 1 left shift 3, and this is nothing but 8. So 1 0 0 0, and now because of all these three, everything will be becoming 0, and this bit will be retained. It will be retained. But as you can see again that the SB1 and SB is pointing to 2 and 2. We do not need any number of ones, right? So it will again fall in the else case. It again falls in the else case. Here it falls in the if case. So again fall it in the else case, and it took the answer from which part? From this part. From this part. We did not flip it. So took the answer from set here. The actual set that was written, I want that set only. So I will say that the previous answer was 0011, and XOR it with the set. So it will be 1000. XOR nahi, or it will be this, or it with the set. So it will be, if you do the or, it will be 110 and 1. And that's our answer actually, if you see it. This is our answer. This was our answer, right? So 9 and 13. What we were getting as the answer. Oh, it was 1011. It was 11, right? Okay. And as you can see, it again come as 1011. So 11 is our answer. So the code which I just wrote, it will work for the case if the SB1 is uh, like the count of A is less than the count of B. So I will write this pseudocode in my code, and then we'll go ahead with code with the last case that is still remaining. So if a set equals to 0, I have to take the answer part from mask, right? So this is the shorthand operator I'm using. In my last previous video, one of our subscriber get lost because of this shorthand operator. So this is nothing but, this is okay, I'll just write it. This is nothing but answer or mask. It's same, right? And since we have used one number, the count of 1, So I will reduce it, that S B minus minus, right? And if that's not the case, then I have to take the answer from set, right? So I will say that answer or equals to set. And what I am doing here is including the same ith bit of A in answer, which is actually X, here, right? Okay, and here what I'm doing, that I'm including the mask in answer. And why is it so? Because I flipped from 0 to 1, right? 0 to 1 to make the number of ones in X equals to the number of ones in B, right? So let me write that also, why I do the flipping, to make the number of ones in X equals to B. So I hope this is very clear to you now. I'm mentioning, so there are some spelling mistake. I'm not rectifying that because that is not our main agenda here. Okay, so we have handled the case where the set bit, if the count of set bit in B is greater than A. So what was that our case? So let's check with our compiler. So 9 and 13. So let's input that test case manually, and we will see that 9 and 13, right? So let's run it. So if the output comes as, what was the output, by the way? It was 11. If the answer come as 11, so my output is 0. Okay, so I have not returned answer here, right? Let's return the answer. Now let's verify again. So my output is 11. Great, guys. So we are good to go with our third and the final case. So let's start. So what was our final case, man? Okay. So let me see to it. What was our final case? So our final case was this number. Okay, so it was 111. It was, let me use blue color. So it was 111 and 1100. So it was A, it was B, and I stored the count of set bit in B in SB1 variable, that is 3, and SB is pointing to 2. You can see that the count of A is greater than count of B. Okay, so for I equals to 0, the A is 1, 1, and 1, right? So what is the mask? So mask for this thing is 1, right? This is mask, and I will do the masking thing here, and I will make the XOR operator, no, the AND operator, to retain just this bit to retain just this bit I'm pointing at. It will be 1, and rest of all of them will be 0, right? So what's the case here? That okay, so what manually we did here was, we just have to flip it to 0, I guess, right? We just have to flip it to 0, right? Yeah, as you can see my second pane screen, for 7 and 12 the answer was 110, right? So let's do it. So it has to be flipped into 0. So what I can do now, what I can do is, okay, so I'll just make a one more case here, that else if, I'm writing this code here, right? So else if is set is not equals to 0, है ना? If it's not equal to 0, and the case was that SB1 is greater than SB now. That was our case. So what we have to do, since this is 1, we need to decrease this count. We need to decrease it to 2, right? Let me show with different color now. So we need to decrease it to 2, right? So I will just write that thing, that SB1 minus minus, and we'll move ahead. So I is equals to 1 now. And again, this is 1, 1, and 1. And now the masking is 2, right? The mask is 2, so it will be masked with 1 and 0 here. So this bit will be retained and everything else will be 0, right? Okay, so here the SB1 and SB was pointing both at 2, and as you can see that set is still not equals to 0. This is our set still not equals to 0, but the SB1 and SB2 is now equal, right? So it will fall into the else part, where it was saying that answer is equals to answer or set, because we actually need this thing now. We actually need this thing, right? So we need to take this in the consideration of answer. So the answer was pointing it to 0, and it will do the or with the set thing, right? So it was answer and this is set. We did the or and we found that the answer is updated to 1 and 0. So let's do the dry run for the last iteration, that is I equals to 3, and we were at 1 1 and 1. So this is the bit that will be retained due to the masking, that will be pointing to 2 power 3, that is 8, and the binary it will be written as uh, so it is 2, right? It is 2. It will pointing to 4, and the masking will be 4 written as 100 in binary. The this bit get retained and rest of the things are 0, right? And since the SB1 is pointing to 2 and SB2 is 2, right? And set is not equals to 0, right? Set is not equals to 0. So it will not fall into the case of this thing. This was actually for the third case, right? So it will not fall into this case, and it will fall into our else if part. So I just need to mention this else if part here, and this thing, this set will again be the part of our answer. So previously the answer was 1 and 1 0. This was the previous answer. I'll just or it with my current set now, that is 1 0, that is 1 0 and 0, right? I will or it and it will say 0 1 and 1. So 110 is our final answer, that is pointing to 6. And if we just verify it from my dry run, it was actually 6, right? For our second test case, was second test case, I guess. Yeah, 7 and 12. So 6 was the answer. So the only thing that I need to mention is here one else if part, that that if it falls into this another equality case. So I will just copy paste from above and I will write it here. But this time this set was not pointing to 0, it was pointing to not equals to 0 case, as you can see here, right? For the first iteration it points to 1, but for the second iteration it points to 2, and for the third iteration it points to 4. So it is not pointing to 0, and it should be the case that SB1, the number of set bit in A, should be greater than the number of set bit in B. So what we need to do then, we just need to decrease the count, right? So we will decrease the count SB minus minus, right? SB1 minus minus, actually this was in greater format, in the larger value, right? So that is it. So let's run the custom test case for this thing, 7 and 12, and if that passes, then we are good to go and submit, when we will submit the code. And before submitting it, we will see what the time complexity is getting finally. So your output and expected matches. So guys, we are done with this code, I guess. uh, let's first discuss the time complexity and we will submit the code. So the time complexity will be, since we are finding this set bit, so that is taking, and we are always running a while loop, decreasing it by 2. So it will be log of n, or let's say log of what, a, I guess, log of a, right? Log of a, and suppose we are finding log a and log b both, so the maximum of it will be the time complexity. So let's say max of, actually this while loop will only take log of n, but since we are using this set bit to find the number of bits in a as well as b, so right, the maximum time will be taking from log a, and log b will be the overall time complexity, right? So let me just cut paste it here and copy paste it here. So this will be a time complexity, I guess. So there we are nothing, just running a for loop of O of 31 time, and these are all the tasks of O of 1. So the final complexity will be the max of log A and log B, which is exactly mentioned by here in this expected time complexity. Auxiliary space will be obviously O of 1. We are not using anything, just instead of variables to store the answer and all. So it will be O of 1. So let's finally submit this code and end this video. So that was a very tiring session for me. Okay, finally we had our submission completed. So again, if you are new to this channel and if you are liking my content and the way of teaching, and if you are maintaining a streak, learning and growing with me, please like my channel and subscribe it, so that we can make our next video journey ahead with full energy. Few last thing, that this is my DSL repository. You can start and fork to get help with the source code, and that's my Instagram channel. You can connect to me here 24/7 for any doubts and guidance if you may have. And that's it, yeah. Tab tak ke liye, till then, keep studying, keep growing, and bye bye, and take care.